Hi everyone. We'll start the new chapter on functions, chapter 7. So it will cover the graphing of power functions where the rational non-integer index. We also review and extend some of the functions that we have done, some difference and product of functions, addition of ordinates, one-to-one functions with some of their features, um, hybrid functions, inverse functions, and also transformations. We also use functional equations to describe properties of functions, and we will use parameters to describe families of functions. Now, the two exercises are covered today. 7a is about power functions, and 7b will be inverse functions. Even if it's not on the first SAC, we're gonna review some concepts like domain, range, graphing, transformations that can still be useful for everything that is covered from up to chapter 6. So let's look into more details about power functions. So before we combine variations of powers, let's look at a negative power which is in fractional form, and the denominator of the power is an odd positive integer. So do remember, when you have a negative power, you can write it as a positive with the denominator being a root function. So if n is odd, as it is a reciprocal function, you will have to exclude 0. So the domain will have to exclude that value. What it means is you will have an asymptote of equation y equals 0. Also, when you have that that form, when x is become very large or very small towards negative infinity, you can see both curves will get close to the x-axis, which is the equation y equals 0. So that's your a second asymptote for the graph. Also, what you can see that the function is odd. If you substitute negative x and you rearrange that expression, you can take out the negative 1 factor outside the power function using your index laws, and what happens is having negative f of x tells you that the function is indeed odd. Same function, the denominator in the power is now even. Being even, you can let's see, this is an example of a graph in red that will include, for the domain, you will have to take only the positive values and exclude 0 as well, so it's going to be r plus. That will give you a vertical asymptote, and also when x is converged towards positive infinity, y will become that function will become very small, so the equation y equals 0 is also a horizontal asymptote. Few examples. So you have a function given, you need to be able to sketch it. So before you sketch it, always find informations like domain, range. Good idea sometimes to find also your intercepts, but also things like asymptotes. So you would use your CAS calculator to be able to complete that. So I would pause that and try to do that yourself. So type that into a graph page, observe your graph, and try to answer those questions. Alright, so as we continue, this is the graph. From reading the graph, so obviously it seems from this graph there's nothing on the left hand side. Make sure you do have a zoom out, just in case you're missing out some of the curve. But knowing the power is even, I know it does not include the negative side, so from the previous slide you should know that it's going to be R plus. The range is going to be also R plus. It's converging towards a value, and that's coming from this equation. As x becomes very large, that y value will converge towards -1, so that will give you the range. You can't just rely on this graph, you will have to also look at the rule. There is no symmetry on this side from the y-axis, from the x-axis, or both, so it's neither odd nor even. Again, another example. So here, let's say you do again, you can use the cast to graph it. So you can see you have those two parts similar to hyperbola. Now notice you have asymptote. So you have an asymptote here that is vertical, so that's x equals 0. That will help you with the domain. Looking at the rule, it tells you that the horizontal asymptote is y equals 2, so we can get the domain and range. Alright, now you don't have any symmetry from the y-axis or towards the x-axis due to the vertical translation, so the function is neither odd nor even. Alright, now let's look at a function that will combine a fractional power with a numerator and a denominator. When they are both positive integers, another way to rewrite this is to rewrite in root power form. So separate the numerator and the denominator in the fraction. Numerator will give you your power, and the denominator will give you your root. So looking at your root first, you can see that depending if it's odd or even, you can narrow down the domain. So when it's odd, think about it as a cubic. Even, think of the square root. Okay, now square root. Yeah, with the square root, now it's not a reciprocal, so you do need to include 0 as part of the domain. Alright, so you look at this example. So you denominator gives you a cubic root. Okay, so the cubic root tells you the function that cubic root is odd, but then again it's combined with a even numerator. So by graphing it, you will get a definite better idea. Is the domain is going to be R, the range is going to be from 0 to positive infinity, and here you can see a symmetry, so the function is even. Slightly different power, 3/4. Okay, graphing it, denominator is an even power, so what it means is the domain is going to be from 0 to positive infinity. That will help you to answer the last question. So the domain is from 0 to positive infinity. Similarly with the range, kind of a long notation but still valid, and the function is neither odd nor even. Alright, moving on to composite functions, and also combined with inverse function, kind of useful again for the first SAC. Just to review what you've learned. Notation for a hybrid or composite function, g of f of x. Also, as you combine them, you need to make sure that when you do your first function, the range of that function needs to be a subset, or at least equal to the domain of the second function. Another way you can write this is the domain of the composite function is going to be equal to the domain of f. With inverse function, so you need to make sure that the function is a one-to-one. Graphically, you do a your horizontal and vertical test. You will have the notation, so that's the definition of the inverse, and which is also when you apply f, you get f of y equals x. Now, what it means is x has to be an element of the range, and the y needs to be in domain of f. So you need to swap those two around. Alright, so some of the application, how to express h of x as a composition of two functions. So you have this writing, so you can, the first function f of x is inside the square root, so that's that polynomial. The second function is your square root, so h of x is g of f of x. You can do the same over here. Okay, before I move too quick, so yeah, that would be the notation. Kind of easy practice, just go through the example. Probably it would be interesting, not for this one, for that one, just always have an idea about the domain and range of the composite function, something that you need to be confident to be able to determine. Example 6. So find the inverse of f of x given by that expression. State the domain and range of the inverse. So first, looking at your exponential, if you just look at your exponential, the domain is r, but the range is going to be r plus. So from that, this is a transform function. You can determine the range. So the domain is r. Okay, the range for f is going to be from -3 to positive infinity. That's your y. You interchange x and y, and you rearrange the equation to make x the subject, and I will give you your new function, which is going to be your inverse, and the domain and range will be the swapping around of the domain and range of f. So you have your domain and your range. You have your function in terms of y being the subject. You swap around the variables. You now rearrange that either algebraically or using your CAS calculator. You get log of e bracket x plus 3 over 2. That's fine. And the domain and range will be -3 to positive infinity, and your range will be r. Now notice with the domain, it's from -3 to positive infinity. It ensures that that is always strictly positive, which is how the log to any base will be valid in terms of the domain. Something else that we need has been reviewed as well. It's helpful if you have an interval or in an equation a is greater than b, and you apply a strictly increasing function f to that inequation that is the same inequation. Okay, being strictly increasing also is going to be a one-to-one, and you can have an inverse. Strictly decreasing, you change your inequation. So think about your strictly decreasing function, y equals -x. That is why when you multiply by a negative number, the inequation change direction or sign. Also, it's a one-to-one and also has an inverse. So what it also means is when you have if you have two values that are different on the x-axis, then the y coordinates will also be different, and that it will be across the whole domain of that function. Now, how do you prove that f is, if the function is strictly increasing, how do you know that it is a one-to-one? So first you assume that f is strictly increasing. You have your a and b value from the domain. You write your inequation either way, and then you can apply f, and you have being greater or smaller. Because you have those two statements, what it implies is they have to be different. So because they're different, f of a is different of f of b, knowing that you started with a is different from b, then f is a one-to-one function. And you will do the same. What would implies some properties is, if you have a strictly increasing and strictly decreasing function, if you have f is strictly increasing, then the inverse is also strictly increasing. Similarly, if f is strictly decreasing, the inverse is also strictly decreasing. Example 7. So you have your function that is defined. You need to determine the inverse and state if the functions are strictly increasing, decreasing, or neither. So you write your function, you swap around the variables, you rearrange it, okay, and you can swap the domain and range using the original f function, which is going to be stated down here. And and what you can see, they are, from the graph, they are both strictly increasing. And that's it for today. See you later.